Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be taking our findings from the electronic structure of atoms and applying it to the full periodic table. So one of the very cool things about the periodic table is the generic, periodic trends and how repeatable all of the properties are, specifically most of the properties of reactivity. And most of this reactivity comes from these valence electrons. Because if we look at the periodic table, and we look at all of our valence electrons, we go down each column and they share these same valence electrons, which is really what makes sure that each of these groups share a common reactivity, because valence electrons are going to dominate how atoms see each other. So most of this reactivity is going to be driven from these valence electrons. And again, when we're talking about valence electrons, what we're really doing is we're dividing the system up based on the noble gases. So again, when we look at a noble gas, this means we have a complete set of electrons. So they reach this balance in between reactivity and distance from the system. Everybody wants to look like a noble gas. And so once we've achieved this configuration, these are called the core electrons. And these are all generally fairly unreactive. You can see this with those distance profiles. These electrons are fairly close into the nucleus, and you have to get through this ablative layer of our valence electrons in order to get to them. So once we've gotten past this noble gas configuration, those are our valence electrons. And these are really what are going to dominate our chemical and physical properties and really contributes to our periodic trends and the original construction of the periodic table, because it's based on repeating chemical and physical properties. And all members of a group are going to have the same valence configuration. So one of the classic ones is this noble gas configuration. They all have a completely filled S and P subshell. This gives a more or less filled energy level. And because of this, they're very unreactive. They do not want more electrons, nor do they want to give up the electrons they have. However, once we go to the alkali and the halogens, the fact that they just are one electron off from the noble gases mean that these are the two most reactive sets of elements. When we're looking at our alkali metals, you'll notice they only have one valence electron. This one valence electron is actually held onto fairly loosely, which means that most of the alkali metals are saying, oh, it's just too hard to hang on to them. You take them. And this is the reason why our alkali metals tend to so readily ionize to form cations, because they love to lose this one valence electron. And similarly, our alkali earth metals fairly easily lose 2 electrons. In contrast, we have our halogens. Well, if they get one more electron, well, then they have a complete set. And one of the important parts is that one electron, well, I've already paid my spin pairing energy. It's going to go in with everybody else. I have a nucleus that's fairly charged, so I can take an extra electron. Heck, I like one. So while the alkali metals and alkali earth metals love to lose electrons, the halogens love to gain electrons. And as a result, one of the ways we talk about these systems is that they have a full valence shell or a full octet. And the reason why can really be seen with the halogens, because when we're looking at our valence shell, we often tend to ignore D and F orbitals. And what we're really doing is looking at our S and P orbitals. So I can put 2s and 6p orbitals. And if I have that full valence subshell, well, this means I've got 8 valence electrons, or more commonly known as an octet. So when you hear me talking about octets, what I'm really talking about is this desire to have 8 valence electrons. However, really, in order to describe a lot of these periodic properties, us being chemists, we like to put numbers to things. So we're going to try and come up with a fair number of ways to quantify either how much an element wants to hang on to electrons, if you're talking about something like alkali and alkali earth metals, or how much they want to gain more electrons. if you're talking about things like halogens. So it's this desire to hang on to electrons and where the electrons are around an element that are going to dictate most of our periodic properties that we're going to talk about this chapter. Next time, we're going to be talking about specifically how much nuclear charge each of these electrons are effectively feeling. Until then, take care.